Hello, everyone. Welcome to our Climate Change AI webinar series. My name is Rasika, and I'm part of the Climate Change AI team, and I'm also an assistant teaching professor at Northeastern University. Today, we're going to talk about decarbonizing AI. For those of you attending your first event from Climate Change AI, we're an initiative that fosters impactful work at the intersection of climate change and machine learning by providing education and infrastructure, community building, and advancing discourse in this area. CCAI conducts various initiatives to disseminate knowledge at the intersection of climate change and AI. We offer digital resources and coordinate a range of events, including summer schools, conferences, workshops, webinars, and meetups. We provide grants to support the establishment of programs, and we're actively engaged in policy conferences to foster discussions. Additionally, we bring together a vibrant community that stays informed through regular updates via our newsletter. For more details, you can visit our website, climatechange.ai. By joining our community platform, you'll gain access to valuable information from CCAI and have the opportunity to connect with people interested in various fields of application. Our blog posts are available to everyone and cover a wide range of topics, including research applications and presentations from our team. If you're interested in what we do, you can follow us on Twitter or register to our newsletter, where you will have various updates about conferences, funding opportunities, recent projects and articles, and job opportunities. So this webinar will be organized like this. So Noman will have 45 minutes to present, followed by 15 minutes of Q&A at the end. So add your questions in Slido, and we will try our best to process them as we go. To make this webinar interactive, please connect to the associated Slido platform using the QR code or in the link provided in the description of the YouTube live stream. You will be able to ask your question on this platform and upvote for your favorite ones. The questions will be the higher number of upvotes will be more likely to be asked. So without further ado, let's introduce our speaker. Noman Bashir is a postdoctoral research fellow at the Manning College of Information and Computer Sciences at University of Massachusetts Amherst. He received his PhD in computer engineering from University of Massachusetts Amherst in 2022. His research focuses on decarbonizing societal infrastructure, including large-scale data centers, distributed edge computing systems, and cyber-physical energy systems. His recent work has explored the fairness, equity, and sustainability aspects of systems. He worked on the efficiency and performance of energy systems, decarbonizing residential heating, reducing the cost of cloud computing, decarbonizing data centers, and increasing their efficiency, and enhancing the performance of edge computing systems. So thank you for Noman for being here today. The floor is yours.
Thank you, Rasika. I will share my slides. Please let me know if you are able to view those. Are they visible? Okay, thank you. So hi everyone, as Rasika introduced, I am Noman from UMass Amherst. I'm currently a postdoc research associate. And today I will be talking about decarbonizing AI, the good, the bad, and the ugly. So it's basically talking about what are the good things happening in this space, why do we need to do this, and what are some of the pitfalls that we need to be aware of as we work towards decarbonizing AI. So first, I would like to give a brief overview of my research. It spans, roughly speaking, like 3 domains. First one is cloud data centers, and second one is cyber physical energy systems. And then finally, I incorporate equity and fairness into all of these systems. So on sustainable computing side, my work can be broadly classified into like three domains. First one, we look at how carbon attribution, carbon accounting, and optimizations are being done, what different people and organizations and research papers are using as a metric to do these carbon aware optimizations, and if they make sense, should we go down that route or not? And basically, these are position papers that present our views on this topic. Then we have built a couple of systems for carbon aware execution. So let's say if you have an ML workload, a training job or inference, how can you execute it in the most carbon efficient way possible? And for that, you need actual systems that enable any kind of optimizations that you do. So we have a couple of papers in this domain that actually build systems. And then finally, optimizing carbon and energy footprint of computing and AI. So in this class of work, we basically look at how can we actually reduce the carbon footprint. So it's about optimization and algorithms that basically try to reduce the carbon footprint or the energy footprint of computing in general and AI in specific. Then I have had done some work on cloud data centers and resource overcommitment and cost and wait time optimizations in the cloud and power monitoring. So a lot of work that I did in this domain informs the work that I do in sustainable computing. And then this second body of work basically leverages computing for sustainability, about solar performance modeling and forecasting. How can you make energy systems kind of more programmable so that you can deploy things like demand response on actual physical energy systems? I also worked on electrification in sub-Saharan Africa. What are kind of the novel solutions that we can enable there? Finally, my work also, even across all these topics, fairness and equity is kind of an important aspect that I incorporate into my work. It looks at residential heating decarbonization, and so when we are doing these kind of energy transitions, we should not ignore fairness and equity. How can we make this energy transition more equitable? So my work is kind of quite diverse, but it has a very central theme of resource management and incorporating equity, fairness into all of these domains. And for today's talk, I will be focusing on this optimization part, where we looked at some of how can we basically reduce the carbon footprint of training ML workloads. And we have some work in that domain, so I will mainly talk about that. Some of the work, some of the things that I will talk about will also be from carbon attribution, accounting, and optimization to give a broader perspective of how we look at things, and how, if you come across any kind of work in this space, what are the things that you should look out for to actually gauge the importance of that work. So rather than starting with the good, I think I want to start with the bad part, so that later on we can focus a little bit more on the positive aspects and what we can actually do. So the first part is just basically talking about why we are here, how we have gotten, and what is the gravity of the situation. Before I go into any of the details and present any numbers, I want to talk about, okay, what is the carbon footprint of any computing workload, let alone AI or anything for that matter. So it is based on four things. First one is cycles per unit of work. which is algorithmic efficiency. So basically, if you want to do some amount of work, how many CPU or GPU cycles that you need to actually spend in order to, let's say, add two numbers or multiply them. Then the second part is total units of work. How many of those operations you actually need to do. So you multiply them, you get total number of cycles. Then you divide it by computing's energy efficiency. So computing's energy efficiency is that to let's say, one cycle, how much energy you need to consume. So this is basically hardware efficiency. You get more advanced hardware, you get less and less, you consume less and less energy to do the same amount of work. Then finally, its energy is carbon efficiency, which is basically when you use 1 unit of energy, how much carbon you emit. So if you multiply the bottom two things, you basically get how many cycles you get per unit of carbon. So the bottom part is how many cycles you get per unit of carbon. The top part is how many cycles you do. So basically, when you divide these two, you get what is the actual carbon footprint of computing. And this kind of like going to the fundamentals and looking at what actually makes carbon footprint allows us to understand where are the most opportunities possible and where we are kind of like reaching our limits. And if you want to know about like how we look at the individual things that are in this equation, you can read this paper which was published in Hot Carbon last year. So let's go through all of these things one by one. So first one is basically the total units of work that we need to do. Computing's demand is growing exponentially. Society continues to find useful applications. And even though I have not like put ChatGPT or anything like that, you already know that the computing demand for ChatGPT and like AI applications and LLMs is kind of going to accelerate this curve further. So over time, basically, in this graph, we have time on x-axis and transistors shipped per capita as a proxy for computing demand on y-axis. So, and I have augmented the curve with key inventions and applications on this graph. And this is to give an idea how the key inventions in the earlier days were few and far in between. It also shows how there has been a slew of new inventions and applications over the last 2 decades. And in my opinion, two of the most important milestones have been, I think, so far been the availability of personal computers and mobile phones. And second one, cloud platforms where anyone could host useful applications for these devices. And I think the third one would be like the availability of these large language models to public. So all of this coupled with recent explosive growth in ML applications and their model sizes means that demand is accelerating. And there is no end to this. We are only beginning to apply all of these tools to various aspects of life. And as we do that, the demand will keep increasing. Now, the question is, demand is not in itself a bad thing, because as long as you are applying it for useful applications. What matters is how much energy consumption is as a result of this explosive growth in demand. And there has been a lot of different estimates on basically how much energy is being consumed by different data centers. Around 2005, it was predicted that computing's energy demand will double every 5 years. In 2018, the same group of people updated their estimate and said that the energy demand only grew by 6% from 2010 to 2018. So this is basically the bottom line. While this study is widely quoted by industry and other like people who think that we have demand under control, there are other estimates that suggest the energy demand can be anywhere between 200 to 900 terawatt hours. So if we the purpose of mentioning all of this is not to say that one study is better than the other. It is just to point out that all of these are just estimates. And even if we take the most optimistic estimate, which is 6% increase, demand still outpace the gains in energy efficiency. And one of the key attributors to energy efficiency gains was the shift in basically shift of computing demand from traditional data centers, which were very low energy efficient, to hyperscale cloud data centers which have really high energy efficiency, like PUE value of less than 1.1. So however, this was one-time gain. This and other efficiency gains are slowing down while demand is accelerating. This means that the growth in computing demand in the future will lead to a corresponding kind of exponential growth in energy demand. So now the third part is, okay, we have looked at energy consumption of computing, its demand. Now, if you consume some energy, how much carbon you are emitting? That is kind of the third piece which relates it to carbon. So if you look at in this graph, I have basically time on x-axis and intensity change on y-axis. So if you look at the grid level carbon intensity, overall, the good news is that the carbon intensity of the grid has been decreasing in the United States. Over the last 18 years, the carbon efficiency of the grid increased by 2.33% per year, and energy demand increased by 0.6 per year over the last year, based on the most conservative estimate. This means that the carbon footprint of computing actually decreased by 1.64%. This is good news, but only if we take the most optimistic estimate about energy demand and assume that they are accurate. Also, computing is not being used only in the United States, and if we look at places beyond Europe and North America, the situation is not as good. The carbon intensity of the energy in Asia and overall world has either increased or remained constant. Asia is also the region which is experiencing massive growth in data centers capacity, and combine this with the potential inaccuracies in energy estimate, the future does not look as rosy as like those conservative studies would like to point out. So now that I have gone through like these things, I would just quickly bring you back to this part to basically discuss where are the opportunities. So I will briefly say that, like, okay, cycles per unit of work. Even if you develop the most efficient algorithm, you would still need to spend some cycles to do the work. So the gains in that are bounded. While there are a lot of software and ML algorithm optimizations possible, it is still it is going to reach its limits someday. Then computing's energy efficiency is also bounded. To do some work, you will always need to spend some energy. That is just the law of physics. And also, Givon's paradox says that if you make things more energy efficient, it doesn't mean that the demand reduces. So any gains that we have from energy efficiency, they are also bounded. The two unbounded things are total units of work. Demand is going to increase. Crypto mining ML demand is outpacing Moore's law. And it's not something bad, it's just industry has strong incentive to maintain and accelerate growth. Bottom line matters, financial incentives are more important, stakeholders and investors are kind of important, so that they don't have any incentive to reduce demand. So in that case, the other unbounded thing is kind of that gives us hope, which is theoretically you can go to infinite energy's carbon efficiency. If you run on some energy source that is basically zero carbon, you have infinite energy's carbon efficiency. So this is kind of the place where we can get gain. So with this, let's move on towards kind of the good part, what we can do about it. So one thing that there has been a lot of recent work on how to reduce the carbon footprint of computing. And the bottom line of, or the key essence of that work has been that carbon intensity of electricity varies across space and time. And we should leverage that variability. So if I look at the left figure where it is from Ontario, Canada, it is from Ontario, California, and Uruguay. So you see that different places have different amount of variations. And then basically, if you look at the highest point and the lowest point, this one and this one, basically the spatial variations can be up to 30x. So let's say if you are operating in California, you could move to, if you could move to Ontario, you could reduce your carbon emissions by 30x. Similarly, if you just basically shifted your workload from this to this, I think arrows are kind of mixed, but basically even if you were operating in Ontario, if you move your workload from this point to this, because this is a cycle, so you can think of that there will be another low point in the future. So if you move your workload from here to here, you can still decrease your carbon intensity by 6x. So all of the work in carbon aware optimizations basically leverages this flexibility and tries to find the time and space where you could train your ML model or infer things in the low carbon manner. And this right graph is kind of basically showing the variations across different like places. So there are regions which have kind of like these top regions have high carbon intensity, which is x-axis, and also coefficient of variation, which captures how much variable there is. So variation is important for temporal optimization. So basically a lot of regions are here which have high carbon intensity, high variation. But as more and more renewable energy gets added into the grid, we will be moving towards this part like Ontario and like Quebec. If some regions install nuclear, their variability would decrease, but they will also become low carbon regions. So basically the point is that right now we have all different kinds of regions, some very, very high energy regions, like high carbon intensity regions like Maharashtra in India and like even Oregon, they don't have as much variability. On the other hand, we also have very low regions which don't have variability. And then we have California, Ontario, which sit there. So given this variation, how do we see that how we can decarbonize AI? In my mind, I think there are three components that need, like this is like three parts that we need. First is sense, second is optimize, and reduce. And by sense, I mean that you need to know what is the carbon intensity of electricity to make any kind of like these workload shifts across time and space. And there has been a lot of recent work by a lot of companies. WaitAWhile is a non-profit organization that provides real-time carbon intensity information, and they have been pleasure to work with. We have gotten a lot of data from them. I highly recommend them. Electricity Maps also is a really, like we have been working with them. They also provide forecast and carbon intensity information, but they are for profit. And CarbonCast is a tool that academics at UMass built to basically allow anyone to have a carbon information service on their laptop if they wanted to. So this tool is also available online if you want to just like use and deploy your own carbon information service. Then there is this also Repeat service that is, I should have put links, but basically Repeat is from U Chicago. They're also doing like similar things, and they are also trying to kind of predict how solar curtailments happens, and if we can use those time periods to schedule our ML training. Then basically the second part is optimized. When and where should I run? How do you actually determine that? So basic idea, like very, very basic idea is when the carbon intensity is low, you run. When it is high, you pass. And then basically our work kind of upgrades that in different angles. What if you could scale during low carbon periods? What if there was a cost to switching on and off? So like these two works basically look at, like, if you don't have a cost, you can be cost of switching on and off. You can easily do that. But if there is a cost, then you have to kind of analyze the trade-off between savings and switching costs. And we have also work that looks at for using forecasting of demand to save power in GPU clusters. Then final part is, okay, you have an algorithm that tells you when and where to run. How do you actually do that? And we have a couple of papers. EcoVisor is a hypervisor that basically allows you to run your applications in a carbon aware manner. And Gaia is a cloud based scheduler. So basically, these are the two systems that are out there as open source. If anyone wants to use them to deploy their applications, they can do that. So I will talk about basically this carbon scalar project in detail. So if let's take a look at this left figure to motivate. So this is kind of, let's say you have 2 units of work to be done. And this is your time, like you have 3 time slots. In the first time slot, carbon intensity is low. In the second, it is high. In the third, it is again low, but not as low as the first one. So if you don't care about carbon, you just like start in the time slot 1 and you complete at the end of time slot 2. Then there is work by people from Netherlands and Germany, which basically uses a very, very simple phenomena that we all know, suspend and resume. Because the carbon intensity here is high, you suspend during that time period, you resume it during the third slot, and you complete it at time 3. So in this case, your total carbon footprint was 110 units. In this case, you have only 30 units of carbon footprint. Now the question is, there is a drawback to this. As you see, you get low carbon, but you have poor performance because your job completion time, or the time that it takes to train your model, it has increased. So what our idea was that machine learning workloads and other kind of computing workloads have some scalability properties. So if you look at ML ResNet 18, which is like this black line, this graph has number of servers or GPUs on x-axis and normalized throughput on y-axis. And it basically says that if you double the number of servers, you get almost double the throughput. But it is not exactly linear, as you see that, because when at 8 servers, it does not reaches at 8. And this is because as you add more and more servers, there is more energy going towards communication. So you don't get kind of like linear increase in throughput. So if you look at, let's say, this blue ML VGG16, it has quite poor scalability curve. So, but basically different models have different scalability curves, and as you add more and more servers, it will not scale as good. And our idea is basically, if I go to this slide, that when there is a low carbon slot, what if I ran at 2 or 3x during low carbon slot? Then basically I won't need to wait for the next carbon slot, and I may be able to finish my workload here. In that case, I may even increase my performance by reducing job completion time. And definitely low carbon would be possible. So what determines how much you can scale here, ML training workloads, how much you can scale them, is this scalability curve. So if you have theoretical kind of linear scaling, you can just add infinite number of GPUs and you will get infinite, like, or let's say you add 1,000 GPUs, you get 1,000 units of work done. There is no loss. But if you have sublinear scaling, which is kind of like all of these, some are more than others, it would basically be that as you add more and more GPUs, the amount of additional work that you get reduces. So basically, you are being less energy efficient. So now, when you determine how much to scale your training workloads, you basically have to decide, weigh the cost of basically this part, which is the loss of energy efficiency, and how much you are gaining by operating in the lowest carbon slot. So basically, this is kind of the essence of this work. It determines scaling properties of ML training workloads depending on their this elasticity curves. So this is carbon scalar in action. So on the top graph, we have carbon intensity, which is varying over time. Then the middle graph is basically GPUs or servers, and it plots the working of different options. So first one is carbon agnostic. You start at time slot 0 and you keep running, and it finishes at some point. And if you look at the cumulative carbon, it increases kind of like linearly. And then this is the total amount of carbon. Then the second one is kind of suspend. Let's look at the suspend resume. So whenever it defines a threshold here, if the carbon intensity goes above the threshold, it basically stops running. So basically, here you see that there are 0 number of GPUs allocated. And as a result, because there are a lot of variations, it ends somewhere here, like around 190 seconds or hours, sorry. In final carbon scalar, what it basically does is that whenever there is low carbon slot, rather than resuming at 1x, it increases its number of GPUs to parallelize, and it finishes much earlier. Still not as quickly as carbon agnostic, but it has carbon footprint much less than carbon agnostic. It may be slightly higher than this because of the energy inefficiency that you are using. This is kind of the most energy efficient execution, but this may be carbon efficient execution, but it is still losing some energy. If I look at different models for like Canada, Ontario, so basically you could reduce the training footprint of your ResNet 18 model by, I think this is kind of, this is carbon agnostic, and all the other values on the top are basically relative to carbon agnostic. So suspend resume basically reduces by 17%. Carbon scalar can reduce the carbon footprint by 43%. And secondly, as I mentioned earlier, it depends on the scalability curves of your ML training model. And as we saw in the previous graph, that VGG is kind of not as scalable. You see that it does not get significant benefits. Then, if in addition to the model, obviously you must be wondering that because different locations have different carbon intensity profiles, so the savings that you can get would be different. It would depend on not only how much variations are there, but also the magnitude of the values. So here we have this graph which have a bunch of locations on x-axis, and on y we have two y-axis. Left y-axis is carbon savings in percentage, and the right y-axis is carbon saving absolute. So I want to point two things from this graph. First one is that there are variations across spaces for sure. The second one is even for regions where you won't be able to get a lot of carbon savings, let's say here 20%, or for Tokyo it may be, I think, 5% or so, the absolute amount of carbon that you save, or when training, I think this is for ML ResNet 18, the absolute amount of carbons that you save could be significantly more. So if you are kind of restricted toward in operating in a given region, yes, ideally you would like to move to a kind of low carbon region. Maybe Sweden, where you have very low carbon emissions. Like this dotted, like the line is basically that. So if you train the same model in Sweden and Iceland, you have very low. So you would want to operate there ideally, but those data centers may have capacity restrictions, and you may not be able to move there. So in that case, if you are restricted to all of these regions, you still could use temporal variations to reduce the carbon footprint. And in that case, you could look at absolute carbon, because at the end of the day, every kind of unit of carbon is important that gets added to the environment. And then, so this was a system that actually you give it workload, it optimizes it for you, and it actually runs it. I am not talking about the system side, so therefore I am like kind of like just focusing on the optimization, and you can find more details of the system in the paper. But still, that is when you actually have to deploy a model and it will find best schedule. But what if you just want to first understand, like you want to deploy something on cloud and you want to understand what would be the emissions if I was to deploy this particular model with this particular configurations in a particular region. So we developed this tool. I will be able to share the link later on, but I could not because of it's under review. But basically what it does is that if you are just looking, you could specify your job configuration. You don't have to provide the profile. We have kind of loaded profiles, but you just can tell that I am using this ML model. And then basically how long it will take to run, when do you want it, how many GPU resources you have, and which are the locations that you want to evaluate it in. If you give all of these things, we get carbon intensity data from electricity maps. So it gives, and also we tell the resource prices, like, okay, how much a GPU costs and in different regions by different cloud providers. So it will basically give you two things. First, it will give you a schedule that you should run your workloads in these times. And then also it will give you total estimated emissions, also total estimated cost. So basically anyone who is not going to deploy the system but want to just get a feel of how locations matter, how different models matter, what are the costs and carbon savings trade-offs, they will be able to go to this tool and try a couple of things before they actually deploy. Okay, so the final part of my talk is about what should we be aware of when we are doing all of these carbon optimization. And for that, I would kind of go back to carbon accounting and attribution methods and how they are being done. So on the loosest end, you must have heard of companies saying that we are carbon neutral since inception or something. So for 50 years, we have emitted some carbons, and then they buy some offsets, basically, which are location and time independent. And they may be, okay, we planted these many trees and things like that. So they are kind of losses, and there has been a lot of research work that proves that they are not effective. A little bit stricter method of carbon offsetting is annual, and it is still location agnostic. So company would say that we will be offsetting our carbon on annual basis. It would do that by either subsidizing renewable energy generation at some other part of the world, or still use tree-based or any traditional carbon offset mechanisms like carbon credits. Now, recently, Google and some other companies have come up with this 24/7 carbon offset. And what they do is that they are much better. What they do is basically they say we will match our demand with the energy or green energy from renewable energy sources on the same grid on hourly basis. So basically they would generate same amount of energy on the same grid, let's say California, on hour by hour basis. But one thing about this is that it is still a financial mechanism. It's not that those renewable energy producers are physically powering the data center. You are still relying on the grid to back you up when, like, let's say, within 1 hour, solar dips a little bit or things like that. The strictest form of accounting would be zero carbon grid. Basically, what our position is that 24/7 matching is awesome. It's much better than anything else we have had. Carbon emissions should probably be attributed to all loads based on their energy consumption. So let's say if you have a grid which has 30% renewables and all of the rest of the generation comes from fossil fuel based resources, a company should not be able to come sign a contract with renewable energy producers and say that we are carbon free while the rest of the grid is running on fossil fuel. It should be that if you are connected to a grid, basically you should proportionally share the emissions. I understand like this may have some like kind of it's harder to grasp when it comes to accounting and people like financial incentives, but ultimately you can only be carbon free when the whole society is carbon free. And if you are the one claiming earlier, like the first kind of 30% of renewables that are much easier to add or integrate into the grid, then it is unfair to the late adopters of energy, solar energy, that who are either barred from adding renewable energy or they have to use storage because the cost of integrating renewable like increases kind of exponentially as the penetration level increases. So basically, what we are like the point here is that all carbon offsets subsidize renewable energy to some extent, but stricter the carbon offset, the better. These are kind of like, okay, you are still doing something. Strict this 24/7 matching is the best out there, but ultimately our goal is to have a zero carbon grid which does not emit any emission. Then the next part is which has generated heavy debate nowadays, which is how like there is this concept of embodied carbon and operational carbon. So I will quickly kind of tell what they mean if for people who may not be aware. So operational carbon is you do something, you are operating like your data center, you are consuming energy and anything. It is kind of also called scope 1, 2 emissions, which are basically carbon emissions from directly your operations. And then embodied are scope 3 emissions, basically, which are part of the supply chain. And if you were using some chips manufactured by another company, whatever was used, however much carbon was emitted as part of like producing those chips and all the other equipment that you need. So our kind of like point is this. Ultimately, embodied carbon is just operational carbon, just for someone else. So if everyone reduces their operational carbon, embodied will go away. Currently, optimizing for embodied by all these like companies and even some standards are being developed that kind of mix embodied and operational. They are a bit misleading in a sense that a company's embodied to operational ratio depends on where you sit in the supply chain. So if you are at the bottom of the supply chain or you are making end product, it means that you are only very small share of the economy. So your operational emissions with respect to the rest of the economy would be much less. So your embodied would be much higher. And that would give an indication that, okay, you should optimize for embodied, it's more important. But basically, optimizing for embodied is essentially saying your operational emissions are more important than my operational emissions. It's like what I am trying to say is not that you should not look at embodied carbon. Definitely, it matters how many servers you use. If you can use something longer, that is better. Which manufacturer you buy from, that also matters. So all of these things matter. It's just when people start comparing embodied and operational and kind of coming to a conclusion that embodied is more important because its magnitude is bigger, that is where kind of the problem comes. And they should not be added together because they are part of different scale. So we have a paper in Hot Carbon 23, which kind of discusses some of the myths and potential pitfalls of optimizing purely for embodied carbon. So what does all of this mean for sustainable computing? So we have this carbon intensive grid. We want to go to carbon free grid. What do we need to do actually? The prerequisite is basically clarify misunderstanding. And by that, I mean, you must have read that there are 100 different terms that are being used in carbon aware or decarbonization process. Some will say that carbon free, we are carbon neutral, we are zero carbon, 100% renewable. They all mean slightly different things. And they complicate the scenario. And basically I have read so many different kind of terminologies that even despite working in this domain, I don't fully understand when I see them. So what we need to do is that we need to understand and clarify all of these terminologies. What does actually 100% renewable mean, or zero carbon mean? How is zero carbon different from carbon free? And then kind of the next step is visibility. You cannot do anything without being able to look at what is the footprint of my actions. So what time electricity maps and other things have done has enabled visibility into it. So we should leverage it. And that's like kind of a good thing where I am quite hopeful that this has become relatively easy as opposed to like I thought it would be quite difficult to actually get and estimate how much carbon footprint of your electricity is and ultimately thermal training or anything. Then basically we should shift focus from energy to carbon because in one of the slides I mentioned that you may be more energy inefficient, but you may be carbon efficient. So historically, our focus has been on energy efficiency, which makes sense because historically cost has been the basic like kind of motivation for companies or anything. If you reduce your energy consumption, you get less bills. That is good. Also, previously, carbon intensity of the electric grid was kind of assumed to be constant. So if carbon intensity is constant, then every unit of energy that you reduce, it means that you reduce 1 unit of corresponding unit of carbon. But as it becomes variable, they start to diverge. So just reducing energy consumption, basically the most energy efficient operation may not be the most carbon efficient operation. And we have another paper on that in Hot Carbon this year, which basically looks at the tension between the two. And finally, we should leverage computing flexibility, change how we operate, use computing to balance the grid. I think some of you may already be working in this domain. Then I will quickly go through like what some of the things, just list out the things that we are working on. I think there are 3 things that we are looking at. Large language models and basically fine tuning of models. So far our work has been kind of if you are training model from scratch, even though that also applies to fine tuning, but still we want to see if there are any nuances in not training things from scratch and if there are optimizations that are possible over there are different. For large language models, my thinking is that, so if you have like seen the carbon scalar work that we presented, basically when you stop when the carbon goes high, you are basically checkpointing all the state, whatever is in your memory, you are checkpointing that. But with large language models and these bigger models which have massive memory footprint, that would be kind of impractical. It would take so much time and energy to save the state that any optimization benefits that you get may not be able to outweigh the energy footprint. So basically, to be honest, I have not really looked into more details, but my initial impression, like I don't have any clear thoughts on how, like, what are the potential opportunities there. There are definitely, because one thing that, like this paper from Andrew Chan, again in Hot Carbon, mentioned that as you deploy more and more applications like ChatGPT and its derivative applications, the footprint of inference is actually going to outweigh the model training. Because at scale, your inference would be consuming a lot more energy than training. So over there, we can do a lot, I think. If you don't have kind of strict latency requirements, you could basically move things to operate in within some geographical boundary to do that. And then final, we are looking at federated learning. And to conclude quickly, the bad thing is that computing AI demand is increasing. The good thing is the recent focus on AI's carbon footprint. There are opportunities in all of these: sense, optimize, reduce. There has been a lot of work on that. And the ugly part is that we need to be very careful about what we optimize and how we account for carbon emissions. And these are some of the links that if you want to kind of know more about the work that we do. And these are a list of my collaborators that I worked with to as part of like all of the works that I found. And with that, I am open to questions.
Yeah, thank you so much. Feel free to leave that up if you want people to look at the links.
Sure.
Let's look at some of the questions. So in terms of the bad and ugly of decarbonizing AI, what do you think about the regulation of it?
So one thing is that one thing that would kind of solve all of this problem is carbon tax. But countries like US are unlikely to ever impose a carbon tax because it hurts legacy businesses who are still fossil fuel powered, or at least not in the near future. So then what is kind of our options? Even with last year's like climate change bill that Biden administration introduced, they opted for indirect incentives. So indirect incentives were like these: if you install renewable energy, you get this much subsidy. They are all well and good. So on that side, like we won't have carbon tax, so there are indirect incentives, but we would need to understand what kind of behaviors that they lead to the indirect incentive. Because if you have carbon tax, that's very simple. You reduce your emissions, you tax at every segment of the supply chain, and you kind of solve that problem. But with indirect incentives, we need to understand what behavior they lead to. Second part is there is a recent, I think, proposal from SEC to allow, basically requiring companies to report their emissions. But it is still like, while it is a good thing currently, and all of these companies have been doing things kind of voluntarily, but having like this kind of framework which requires them just like their financial reports would be nice. But still, while at the high level that is nice, the specifics of that would actually determine: are you required to have, like, how do you even measure the accuracy of those values? Because currently I don't, to be honest, I don't trust any value for embodied carbon because they are all just very, very high level estimate, can vary from one company to the other one. So that is kind of the current problem. So having at least stricter regulations about the accuracy of the information would definitely be helpful.
Okay, thank you. Let's go to the next question. Okay, so what are machine learning techniques used for decarbonization, and how do you think decarbonization helps global warming?
Okay, so on the ML for kind of decarbonization, AI for decarbonization, there are, I think, immediately two things that I personally work on, so I can say more about that. One part is transportation. So we are looking at ride sharing services. So ride sharing services have this huge deadhead miles. Deadhead miles are basically when a driver is either going to pick someone up or she has dropped someone and they like going to some other like place to pick the next one. So these are the time periods when they don't have any passenger in it. So building actually like online algorithms. For that, I work with Mohammad Haji Ismaili at UMass and Adam Weirman. Basically, this work looks at building carbon-aware ride assignment algorithms that reduce deadhead miles. At the same time, we need to also, there are like in ride sharing literature, there is also impact on equity because it has shown that black passengers are probably, or the neighborhood with disadvantaged communities are likely to face longer waiting time. On the driver side, we are considering that, let's say, if we are assigning rides based on how much emissions you emit, a person with disadvantaged background may have a car that has higher emissions and may not get any ride assignment. So in that, like basically trying to reduce emissions while making sure wait times don't increase and also incorporating equity angle. So that is kind of a really nice mesh of things where these data-driven ML and AI online algorithms are helpful. Second thing that I work on is there is a lot of work going on in reinforcement learning for building controls at city scale or even individual building levels where you basically control HVAC or other flexible loads that allow you to reduce carbon emissions. And similarly, there is some work about EV charging. Where do you charge EVs? And if you have a lot of distributed set of EVs they are charging, how do you coordinate their control so that the grid is not impacted? I think these are kind of the immediate things that come to my mind. And final thing is basically so far data centers have been just considered, and this is not like me saying there has been a lot of work on it. Um, Data centers have been just considered as a load that cannot participate in the decarbonization process. So if you have a data center that can respond to signals from the grid, it is kind of like grid connected data centers basically, then they could act just like storage. So if you could quickly up, like turn on, turn off servers, which you can do that really quickly, or at least their operating level, you could actually increase the sustainability of the grid as opposed to being a negative impact on the grid. So think of like having more and more data centers, and they could actually stabilize, provide frequency response, and any type of auxiliary services that are that could be provided by storage. So I think there is a lot of like kind of potential. One thing is, I think this is how it kind of goes with technology with because currently we with ChatGPT, I am not 100% sure how much of the actual workload that is there or any LLM model, how much useful work it is doing. Because previously with ML training and all, that was kind of in the hand of people who were working on something. They were using ML model, AI models to optimize something. No one was just training model out of like their own, like just like, okay, how does training of a model looks like? But with inference, that is kind of out of the control of scientists who actually are working on it. So then there are some concerns about, I think, how would that impact? But other than that, I think ML and AI is an awesome tool to decarbonize like various sectors. And I'm sure there are 100 other examples I just presented too.
Yeah, absolutely. So unfortunately, we are out of time. Sorry.
Yeah.
But thank you, Noman, for this amazing presentation. And thanks everyone for attending this webinar. The next one will be on August 31st, and we will talk about AI for climate policies. And we would also like to share that we'll hold a workshop at NeurIPS 2023 in December. You can have more information about this and how to submit your work on our website, Climate Change.